but I'll record it just in case. So we are going to pick up our discussion with in Module 2, which is the central limit theorem. And I did post, oops, let me make sure I share my screen. I did post an updated PowerPoint. Last night it was late because I was late getting it finished, but it is there for you guys to use. And then I can post the workspace. Some students have been asking for that, where we do the work when we get ready. Good morning, Jeannie.
Hi, Laura. I hope your husband's doing okay.
He is. I told Catrice he's actually doing quite well, better than we kind of expected, because we were anticipating a significant amount of pain, but it's been quite manageable. So
that's great.
We're doing
back surgery is no joke. So
oh no, and this is his in his lifetime. This is his third one. So
oh geez,
yeah. We're getting through it, but we're picking up today with central limit theorem in module 2. And I'm trying to get this PowerPoint to go. I did post this updated PowerPoint. The one that's there is good, but it's got a lot of theory in it. And I am going to do a little bit of theory today, but I try to make it practical in the context of a problem, so you can actually see how the central limit theorem works. Because it's actually kind of a neat application, or a neat theorem that is very, very powerful and very, very useful in statistics, which is actually where we start. So the central limit theorem is actually one of the most powerful and useful tools in all of statistics. Because one of the reasons that it is so powerful and useful is that knowing that data, even if your distribution is not normal, because remember last time we met, we talked about the normal distribution and how important it was in the world of statistics. It's one of the, I don't want to necessarily say most popular, but it's one of the most useful or most commonly used distributions. So knowing that your data is going to behave in a predictable way can be a very powerful tool, and the central limit theorem helps us to actually see that. We often abbreviate central limit theorem CLT so that we don't have to continually write out central limit theorem. I sometimes have issues spelling the word theorem anyways, so you'll see that abbreviation sometimes in maybe articles that you're reading, or in the questions on the quiz or homework or something like that. So just be aware that that abbreviation is for central limit theorem. In layman's terms, we're going to get kind of into the technical a little bit more so today than we usually do, but in layman's terms, kind of everyday terms that hopefully you can understand, what the central limit theorem does is it forces any distribution, whether it's skewed left, skewed right, it could be a uniform distribution, even an exponential distribution, the binomial, but it forces any distribution to be normal if a large enough sample is selected. And so you got that little caveat there, if a large enough sample is selected. And there are two different versions, or two alternative forms is the terminology you'll see sometimes, of the central limit theorem. One looks at the means, or the mean, and the other looks at the sum. And we are going to look at both. Quite honestly, in my experience, you often see the version for the mean used more often than the sum. I honestly don't remember right off the top of my head ever seeing the sum version before. But it's actually kind of neat when you see how it works. And so we are going to look at both forms. So we're going to start with version 1, which is the central limit theorem related to the mean, which the notation, remember, for the mean is X with a bar across the top. And this is kind of the technical part. What the central limit theorem says is if we collect samples of size n with a large enough n from an unknown distribution and calculate each sample's mean and then create a histogram of those means, the resulting histogram will tend to have an approximate normal bell shape. Again, basically they're saying if we choose samples that are large enough, we can force any distribution to become normal. So then the question becomes, well, what's a large enough n? And so that size of that sample that is required to be large enough actually depends on the original population from which the samples are drawn. Remember, and I don't know that we talked about it in this course, we usually do in Stat 1401, that typically a distribution, a symmetric distribution, begins to mimic or model the normal distribution when you reach a sample size of 30. So in terms of statistics, the magic number is 30. So when you think about a large enough sample, you want it to be at a minimum of 30. And that might be enough depending upon the original shape of the distribution or of the variable. Okay, if the original population is something crazy, really far from normal, then you're probably going to need more than 30. You know, you might need 60 or 90 or 120 or 1,000. But then also it's important to note that we do that sampling with replacement. Okay, so we select one and it goes back into the mix. We select another, it goes, so it's done with replacement. And I'm going to try to show this to you because I really have a neat example where you can really see what this is saying. And I hope that will help you. So the consequence of the central limit theorem is that, again, if we choose those samples large enough, we end up with a normal distribution, and that resulting normal distribution has the following parameters. Remember, the two most important parameters for any distribution are the mean and the standard deviation. So the mean of the central limit distribution is the same or equal to the original distribution, and the standard deviation of the central limit distribution is equal to the ratio of the original standard deviation, and I say a spelling error, of the original divided by the square root of the sample size. And again, those are some formulas that I'll get you familiar with as we go through the lesson. But I want to try to show this to you guys. I really have a great example where I can try to prove what this central limit theorem of the means is saying. Okay, so there's a little bit of theory here, but I think the visual is going to help you. Okay, so years ago, I had access to student social security numbers, and so I pulled some information. And you may not know, but your social security number is a 9-digit number that's assigned to you by the government. The first 3 digits are called the area number, and those are assigned based on geographical regions. The second set of 2 digits is, they call it a group number. And it was kind of weird because it said they do it, they start with the odd numbers and then they go to even numbers and they rotate back and forth, and that's allocated to an area within a particular state. But the last 4 digits, which are the serial number, are supposedly assigned at random. So that's what we're going to look at. I was able to access the social security numbers for my students at that particular time, and this was, gosh, probably 10 or 15 years ago. So I had 131 students, or 131 people, and I took the last 4 digits of their social security number. Okay. And I entered them in individual columns. I can even show you. Let me go out, see if I can pull up the spreadsheet so you can see how I had it set up, so you can kind of see what I did. Okay, so I entered into Excel. In the first column, I had the first digit. In the second column, I had the second digit. In the third column, I had the third digit, and the fourth column, I had the fourth digit. So I had 4 columns of 131 people. So 131 people, 4 numbers from each. So I'm selecting a sample of size 4. Okay, because I have 4 numbers. So I have a sample of size 4. So 131 people, 4 numbers each. That's like 532, I think. I've got it on the next slide. Okay, so if we look at that, those individual numbers, here's the histogram that we get, and they're color coded. So, because I had to do it column 1, column 2. Okay, but this is the histogram of the original population. If I look at those 524 individual numbers, because I had 131 people, 4 numbers for each person, that's 524. Look at this distribution. I hope you realize that that distribution is not normal as it is given, okay, or as it is represented. It almost, okay, if you look at it, almost looks like a uniform distribution. Okay, so visually, this initial distribution appears to be uniform, which actually is kind of a good thing, because that does mean that those numbers are assigned at random, because they're all assigned at equal amounts, equal frequency. If you average or take the mean of those 524 numbers, so you add up those 524 numbers and divide by 524, the mean is 4.45229. And then the standard deviation is 2.897156. Okay, did those calculations in Minitab and just brought them over. Okay, then, okay, so we've looked at them as individual values. And it looks like my distribution is uniform. Then I took and I created or found the mean. See if this will let me draw. The mean, I don't think it's going to let me draw, of those 4 numbers. So I would have added the 4 numbers together. 0 plus 1 is 1, plus 7 is 8, plus 6 is 14, and 14 divided by 4 gives me 3.5. Okay, so this column F is the average for each set of 4 numbers, or the mean for each set of 4 numbers. If I look at the histogram for those means, look at what happens. If you look at the mean, the histogram for the mean of those last 4 digits, look what you get. You almost get a perfect normal distribution. The central limit theorem says if I take samples of a large enough size, and our size in this particular proof, if you will, is 4, because I'm looking at 4 digits, and because I had 131 people, that's sufficiently large enough. I went from having a uniform distribution to having a almost perfect symmetric normal distribution. That's what the central limit theorem says. If we take the mean for each sample, in this case of size 4, and we look at the histogram, it becomes normal. Now look at these numbers here. The mean of the central limit theorem, this normal distribution, is 4.45229. The standard deviation is 1.475803. We had 131 groups of 4. Now let me put these numbers side by side. Check this out. I mentioned a minute ago that the mean of the original distribution was equal to the mean of the central limit theorem distribution. And we have to change the notation slightly so we know whether we're talking about the original distribution or whether we're talking about the central limit theorem distribution. The central limit theorem distribution, to distinguish it from the original, we use a little subscript of X bar because we're using the mean. It's kind of like the mean of the means. Because look at this. In this example, the mean of the original was 4.45229, and the mean of the central limit theorem was also 4.45229. I just proved it to you that if you use the means with a sufficiently large enough n, the mean of the original and the mean of the central limit theorem are the same. For standard deviation, I mentioned that the original standard deviation, or let me write it this way, the standard deviation for the central limit theorem, again, we use the subscript of X bar to indicate that we're using the central limit theorem, is equal to the original divided by the square root of n. Now, I think I'm a little bit off on this one because if you look at those numbers, what that means is that my standard deviation for the central limit theorem should be 2.897156. That's the original standard deviation, divided by the square root of 4 because I had groups of 4. So that would be 2.897156 divided by 2. The square root of 4 is 2. And then if I do that division, I get 2.897156 divided by 2 is 1.448578. So I'm a little bit off, but I'm close, guys. Look, if you do the actual numbers, my standard deviation was 1.475803. If you use the formula, it should be 1.448. So I'm reasonably close. I'm in the ballpark. Okay, so again, I'm not trying to confuse you, but again, hopefully that lets you see what the central limit theorem is telling us. What you need to know is basically these two formulas, that the mean of the original is equal to the mean of the central limit theorem, and that the standard deviation of the central limit theorem is the original divided by the square root of n. And again, because we have a normal distribution, so I can then treat my problems like the normal distribution that we talked about last class, which I know was a few days ago. All right, so let's look at an example. I want to show you how to use this. I also want to try to help you see the differences in how this question is worded as opposed to the ones you saw for a normal distribution. This one says the length of time taken on the SAT for a group of students has an unknown distribution with a mean of 3.5 hours and a standard deviation of 1.2 hours. A sample size of n equals 100 is randomly drawn from the population. Okay, so I want to go over here to my paper. I copied this problem over to my paper where we could make some notes. A couple of things I want you to notice. Okay, notice that even in this problem, it tells us the mean and it tells us the standard deviation. What is different about this one is it tells us that we're going to draw a sample size of n equals 100 from the population. If you go back and look at the problems from the previous lesson, two things are different. One, it told us in the previous lesson that my distribution was normally distributed, which notice it does not in this one. It actually says there's an unknown distribution. And it previously also told us that we were going to select a person or an item. Okay, so it's person or an item. You were doing one. So two things happen here. I still know the mean, I still know the standard deviation, but now instead of selecting a single item, it tells me that I'm going to select a group of items, and my group has a size of 100 in this problem. Guys, those little details are really important because that's going to help you know, like when you're taking the midterm exam, you're going to have to decide, should you do a regular old everyday normal distribution problem? Should you do a central limit problem for the mean? Or should you do a central limit theorem, for the sum? So you've got to pay attention to the words, and it may help you. I have the ability on this screen to highlight things. It may help you even to get a highlighter or a colored pencil or something and underline and highlight things. So the questions begin by saying, what is the mean of this problem or this distribution? Okay, this really is given to you in the problem. Now, I know, again, because I'm going to choose a group of things that I want to apply the central limit theorem. And based on the central limit theorem, I know that the mean for the central limit theorem is equal to the mean of the original distribution, which in this problem is given to me as 3.5. So the mean of this problem is the same as the mean of the original distribution, which is given to me and is 3.5. Then it says, and I intentionally worded this question the same way that you'll see it in the quiz, okay, and on the midterm, because I didn't want you to get confused in the wording. So it says, what is the standard deviation you will use for this problem when looking at the average, which is synonymous with mean, of the 100 people? And then it says round to 3 decimal places. It's also very, very important here, guys, when you're doing these problems, that you pay attention to how it wants you to round, because if it wants you to round to 3 decimal places, when we enter the information into Minitab in a few minutes, you need to make sure you use those 3 decimal places, because the answers are predicated on using that 3 decimal value. I'm trying to help you avoid some errors. Okay, so again, we know we're applying the central limit theorem. The standard deviation for the central limit distribution is the original divided by the square root of the sample size. So this one is, for all intents and purposes, is given to you, but it's going to require you to do kind of a basic calculation. So the standard deviation was given as 1.25 divided by the square root of 100. And it reiterates here in the question that you had the mean, or 100 people in the sample. So that gives me 1.25 divided by 10, which is going to be 0.125. So this is my standard deviation rounded to 3 places. Now again, for the most part, those 2 questions, the information comes from the problem. You do have to do a relatively easy calculation there. Okay. Then let me see if I can get the question pulled up here. They're going to ask you some questions. Okay, it says find the probability that the sample mean is between 3.25 and 3.7 hours. And I hope, now remember again, because we started out with an unknown distribution, but we've selected a sample of size n, and we are applying the central limit theorem, I now know that my variable approximates a normal distribution. My mean is going to be 3.5, and my standard deviation is going to be 0.125. So because I've applied the central limit theorem, I know that the resulting distribution is normal or bell-shaped. So I solve the problems just like I did before with a normal distribution, using the adjusted, as we call it, the adjusted standard deviation. So this problem says, and again, I'm going to kind of help if you see a picture. The other thing that you'll notice is this one, instead of just saying find the probability that, it actually says find the probability that the sample mean. Okay, it again is emphasizing that you're doing something with the mean. Okay, so I'm going to draw my normal distribution. So I have my horizontal axis, my normal bell-shaped curve, the mean is in the middle, and it's 3.5. I'm looking for between 3.25 and 3.75. Okay, so I'm between 3.25 and 3.75. So I'm looking for this red shaded region. Now, just to remind you, remember we learned that the area under the curve corresponds to the probability. So I've rough sketched it. So I'm going to go out to Minitab. And we're going to walk through the steps, the same steps we've had before. We go to Graph, Probability Distribution Plot, View Probability, click OK. It is normal. My mean is 3.5. My standard deviation is 0.125 after the adjustment because of the central limit theorem. Options, we're doing a between based on a specified X value. We're in the middle and we're between 3.25 and 3.75. I hope that looks familiar because that's the same process you went through for normal distribution. The only difference we have here is we have to use the adjusted standard deviation. We're really using the adjusted mean, but it happens to be the same. I'm going to click OK. And we get this plot, and I'm going to copy it over to the paper so it's easier for you guys to see. Let me get to where I can copy it. Okay, so here's our graph. Okay, remember you have your horizontal axis, it's bell-shaped. Your mean is indicated at 3.5, and then you can see 3.25 and 3.75. What we're looking for is this value here that's kind of hanging out in space. That represents that red shaded region. So the probability that the sample mean for this distribution is between 3.25 and 3.75 is going to be 0.9545. So that means there's basically a 95% chance that the sample mean is between 3.25 and 3.75 hours. That it takes, 95% of the students who take the test take between 3.25 and 3.75 hours on average.
So let me ask a question. So the way we're going to differentiate this one from the normal, like the non-adjusted standard deviation, is the problem would have normal, it would tell us it was normal distribution initially, and then you would have specific points rather than that sample mean. Is that right? Is that the
it's just gonna say fine. Let me scroll down, Jeannie, because I have an example at the end.
Okay.
It's the same problem written 3 different ways. Let me scroll down to the end of my document here. Okay, if you go back and look from the previous lesson, you could have had a problem that looked like this. The average teacher's salary in North Dakota is $29,863. Assume a normal distribution with a standard deviation of 5,100. What is the probability that A1 randomly selected teacher's salary is greater than 40,000? Okay, so again, it tells you in those problems, it's telling you it's normally distributed. It gives you the mean, it gives you the standard deviation, and you're told that you're going to select one person or one item. The same question is the second one, and I'll mark this one here, is the central limit theorem for the mean. Okay, this is just good old everyday normal. Same thing, average teacher salary in North Dakota is $29,863. We can assume a normal distribution and still apply the central limit theorem. So it tells us to go ahead and assume that it's normal with a standard deviation of 5,100. What is the probability that the mean for a sample of 80 teachers' salaries? So you see two differences. One is talking about find the probability that the sample mean, and you have a group of items rather than a single. So there's kind of two differences to know that you want to apply the central limit theorem for the mean. It's going to use the phrase mean or sample mean. It might use average. The one we were just looking at used the word average, but you know, those are all kind of synonyms. And you're going to have a group of items as opposed to a single. Now, again, for future reference, because we're going to get there a little bit later here today, is this last one is the central limit theorem for the sum. It says the average teacher's salary in North Dakota is $29,863. Again, we're going to assume it's normal with a standard deviation of 5,100. What is the probability that the sum for a sample of 80 teachers' salaries is greater than 40,000? So again, for this one, I kind of recognize that I'm going to do central limit theorem because I have a group of items, and I know I'm going to use the version for the sum because it uses that word in the phrasing. So you've got to really, really, really read carefully. It's not something you can, you know, rush through, skim over real fast. You've got to kind of read every single word. Does that help, Jeannie?
Yeah, that helps a lot. And you said that, I think you said earlier that the sample needs to be over 30, right?
Typically it does need to be over 30 because, you know, in this case, it doesn't explicitly, you know, this one we assume it's normal. Since it told us we assume it's normal, it could be less than 30. But typically, if it doesn't tell us that, it's got to be 30 or more. You okay?
Yep, that helps. Thank
Okay.
you.
Catrice, are you okay?
Yes, ma'am. So far, so good.
Okay, Naomi, I saw you come in. Do you have questions so far? Are you good?
I'm good.
Okay. All right, still the same problem. So we have, you know, the length of time that it takes a student to take the test. And we want to find the probability that the sample mean is less than 3.60 hours. And again, we're still, you know, it's still this scenario we had back up here. So we have an unknown distribution, mean of 3.5, standard deviation of 1.25, but we're doing the sample size of 100. So we're going to apply the central limit theorem. Okay, again, I'm going to draw the sketch here so we can get a sense of what's going on. Again, because we've applied the central limit theorem, our unknown distribution now has a normal, is now a normal distribution. The mean for that central limit theorem is 3.5. We want to be less than 3.6. So here's 3.6 and less than. So I'm looking for this red shaded region. Again, it's once you get to this point, once you've realized, okay, I'm applying the central limit theorem, and you've made the adjustments, if you will, to your mean and your standard deviation, it works just like a regular normal distribution problem. So I'm going out to Minitab. We go graph, probability distribution plot, view probability. I click OK. It is a normal distribution. My mean is 3.5. The adjusted standard deviation is 0.125. We're doing options. This one is a left tail. It was less than, so it's a left tail, and it was less than 3.60. I click OK. I click OK. I'm going to copy. And come back over here to my paper. Okay. And again, so what you're looking for when you're reading this is this number that's kind of hanging out in space. Again, you've got your bell shape. It indicates the mean. It indicates 3.6 and less than. So I get 0.7881. So the probability that it takes a student less than 3.6 hours to take the SAT is about 78 to 79%. This would be the answer that you would give. Okay, one more, and then we're going to look at central limit of the sums. Again, guys, don't overcomplicate it. Again, when you need to be able to recognize that you're going to use the central limit theorem, make the adjustment specifically to the standard deviation, and then work it just like a regular normal problem. Don't overthink it. But again, the benefit that we get out of this is that we have the normal distribution, which is one of the most powerful and useful distributions in statistics. So again, because we've applied the central limit theorem, our unknown distribution is now normally shaped with a mean of 3.5. This one says find the probability that the sample mean is greater than 3.15. So our point of interest is 3.15, and we want to be greater than that. So again, you're looking for that red shaded region that is to the right. So it's going to be a right tail. Okay, I didn't write that on the others, but I can do that for you. This is a right tail. So going out to Minitab, graph, probability distribution plot, view probability. It is normal with the mean of 3.5, standard deviation of 0.125. This one is a right tail because it's greater than, and my value is 3.15. Click OK twice, and I get the graph. And again, I'm going to copy it where you can see it. Okay, it looks like the whole thing is red, but it's really not. There is a little bit of a white region way down here in this tail, just so you can know. But we're looking for this value that's hanging out in space. So approximately 99.74% of the students take longer than 3.15 hours to take the SAT. Okay, if you want me to write that. On average, because we're looking at the sample mean, 99.7% of the students take longer than 3.15 hours to take the SAT. Okay, so that's central limit theorem for the mean. And again, it will say the word mean or maybe the word average in the description of the problem. Okay, let's look at the second version or the second alternative form of the central limit theorem. And again, I have, from my experience and all the years that I've been doing statistics, I tend to see the central limit theorem for the mean used more often than the central limit theorem for the sum. I cannot recall a time when I've seen central limit of the sum used, but I'll have to try to see if I can find an example or an occasion when you guys would use it. And I'm sorry, I've got the yawns. But it kind of basically says the same thing, except it says if we collect the samples of size n with a large enough n from an unknown distribution and calculate each sample's sum, which means to add them together, and create a histogram of those sums, then the resulting histogram will tend to have an approximate normal bell shape. So it basically says the same thing as the previous form, but instead of looking at the mean, we look at the sum where we've added the values together. And again, the idea of, okay, what's a large enough n? It's the same idea. If it's an unknown distribution, ideally you need at least 30 in the sample. If the original distribution is something really wacky that's far from normal, then you may need more than 30. In some cases, they may tell you, like the example that I had at the end there, it said assume a normal distribution. If they tell you to assume it's normally distributed from the beginning, the group could be less than 30. 30 is best, but it could be less if you know that it's normal from the beginning. The formulas for the parameters here are, they're not harder. They're just, to me, they're just a little bit weird, but the mean of the central limit sum distribution is equal to the sample size, how many were in your sample, times the original mean. The standard deviation of the central limit sum distribution is the square root of the sample size times the original standard deviation. So again, you still get the two primary parameters, the mean and the standard deviation, but you're going to have to do a simple basic calculation to determine those using those formulas there. And again, I want to show this to you using the same example of the Social Security numbers. Okay, so again, we have the 131 people with 4 digits each, so we have 524 values individually, and we decided when we looked at that histogram that it appeared to be a uniform distribution with a mean of 4.45229, excuse me, and a standard deviation of 2.897156. Okay, so then if we apply the central limit theorem for the sum, so here's what I did. Okay, remember for the first one, I had each number in its own column, and we do the sum, so we add them together. Okay, so I went 0 plus 1 is 1, plus 7 is 8, plus 6 is 14. I got a total of 14. Then I did the second row, we'd have 5 plus 4 is 9, and so forth. So I added the 4 digits together. And then I looked at the histogram of those values, and I hit the wrong thing, sorry. And look what we get. Again, if you look at the sum of those last 4 digits, you get a reasonably bell-shaped distribution. Now, guys, it's not perfect, but nothing in life is. But you get a reasonable bell-shaped curve when you look at the histogram of the sum of those 4 digits. The mean was 17.809, which looks a little wonky, but I'll show it to you in just a minute. The standard deviation is 5.903. And again, we had 131 groups of 4. Okay, if we put these numbers side by side, I just mentioned to you that the mean of the central limit theorem for the sum is n times the original mean. So let's see what happens if we do those numbers. Okay, the n was 4 because I had groups of 4. The original mean was 4.45229. And if I multiply those two things together, which is what I'm supposed to do, 4 times 4.45229 equals 17.80916, which is exactly what we had. Now, the standard deviation for the sum is the original standard deviation times the square root of n. Okay, the square root of n times the original. So if I look at those numbers, and I did the calculations there, but I'm trying to do them live here. 2.897156 times the square root of 4. So that's 2.897156 times 2, which gives me 5.794312. Now, if you actually figure it based on the actual data, you get 5.903. So again, I'm a little bit off, but I'm reasonably close, guys. I'm in the ballpark. So even if I look at the sum of those digits, or the sum of each group, the central limit theorem works. I still have a normal distribution with a mean that is equal to the sample size times the original mean, and the standard deviation is equal to the original standard deviation times the square root of n. It's the same concept. It's a matter of whether you're using the mean or whether you're using the sum. And again, the whole idea is it's forcing the distribution to be normal. And so then we can solve problems using our normal distribution. So let's look at some of these examples. An example of these. We got about 20 minutes. It says an unknown distribution has a mean of 90 and a standard deviation of 15. A sample of size 80 is drawn randomly from the population. So again, look at what you're given as opposed to, what you know in the past. You're still given the mean. You're still given the standard deviation. It does tell you in the problem that you're going to select a sample of size 80. So I'm selecting a group, which is my initial clue that I want to apply the central limit theorem. And if I apply the central limit theorem, I know that in the end, my distribution is going to be normal. Then the first question, especially on your homework that they ask is, again, they ask you what is the mean of, and they use this funky notation, okay? This funky notation is the way they're expressing the word sum. That's the math notation. That big funky looking E, which is the Greek letter sigma, in mathematics, whether you're in statistics or algebra or calculus, means to add or total something up. So this is telling you to total or sum the X values. It even goes one step further because it says use the central limit theorem for sums formula. So I know that the mean of the central limit theorem for the sum is the original mean times the sample size. So my original mean given in the problem is 90. My sample size is 80. So 90 times 80 is 7,200. Then it asks you, and you really have to calculate your mean and your standard deviation first because you need that information to plug it into your Minitab, plug it into the problem in Minitab. Then it says, what is the standard deviation of the sum? And again, it emphasizes use the standard deviation of the sum for central limit theorem for sums formula. So that formula is the standard deviation for the sum is the original standard deviation times the square root of n. So the original standard deviation is given as 15 times the square root of 80. And we get 15 times the square root of 80. And this is one of those cases where you would really want to pay attention to, do they want it rounded to 3 places to 1 place or whatever. I get 134.16. And I forgot to write down whether that how many decimal places they wanted, so we're going to go with 2. Okay, but it may tell you round to the nearest whole number, round to 1 decimal place. Guys, it's important. You need to pay attention. Okay, so we've determined our mean for the sums and the mean or the standard deviation for the sum. So then we can begin looking at the problems. And it says, the first one says, find the probability that the sum, see it uses the word sum in the problem, of the 80 values is more than 7,500. Okay, so again, the question uses the word sum. So I have my normal distribution, which I know I now have because we've applied the central limit theorem. The mean for the sum was 7,200. This one asked me if it's going to be more than 75. Which again, visually, again, remember that the probability corresponds to the area under the curve, and this one visually being more than is a right tail. So now I'm going to Minitab to do the calculations. Graph, probability distribution plot, view probability. I click OK. It is normal. My mean is 7,200. The standard deviation was 134.16. My options, it is a right tail, and my value was 7,500. Same process you've been doing. Don't overthink it. Okay, okay, and we get this graph. Let me copy it over here where you guys can see it. Okay, so here's our graph. And again, what you're looking for is this value out here that's kind of hanging out in space. So we get 0.01267. So basically there's, for this particular distribution, there's about a 1% chance that the value is more, or the sum of the values is more than 7,500. Okay, so there's approximately a 1.2% chance that the sum of the 80 values or 80 items is more than 7,500. Again, in this case, we're looking at the sum as opposed to the mean or the standard deviation. To me, the sum is a lot harder to kind of wrap my head around because of that multiplication by the sample size. And to me, it's hard to put it back in the context of the problem. I like the mean better. And again, I see the central limit theorem for the mean used again more often than the others, or than this one. But I needed to show you both because the quiz that you have for this week has both types of central limit theorem problems. Okay, so this one is, you still have the unknown distribution, mean of 90, standard deviation, but you're going to select 80 values. And this one is, what is the probability, to find the probability, the sum, again, notice you got the word sum in there, of the 80 values, so you've got a group, is less than 7,000. So again, we know that we have a normal distribution because of the use of the central limit theorem for sum. The mean is 7,200. We want to be less than 7,000. So less than, you'll be looking at this region here. Notice less than, the region is on the left. This would be a left tail. And I'm ready to go out and do my calculations in Minitab. Stat, I'm sorry, wrong one. Graph, probability distribution plot, view probability. It is normal. My mean was 7,200. My standard deviation was 134.16. It was a left tail with a point of interest of 7,000. Is that right? Yeah. I click OK. OK. And we get our graph, which I am copying so you can see it. Okay, so here's the graph. Again, we're looking for this area under the curve, which is the number kind of hanging out in the space. So it's 0.068 6.801. So approximately 6.8% of the sum of the 80 values would be less, or there's a probability that it would be less than 7,000. 6.8% chance that the sum of the 80 values is less than 7,000. I think I got one more. Okay, find the probability that the sum, again, you've got the word sum in there, of the 80 values is between 7,100 and 7,600. So I have, again, I know it's normal because we've applied the central limit theorem. The mean of the sums is 7,200. In this case, I have 2 points of interest between 7,100 and 7,600. So you're looking for this red shaded region. This is a between, or Minitab calls it middle. Out to Minitab we go. Graph, probability distribution plot, view probability. It is normal, mean of 7,200, standard deviation of 134.16. It's a middle, and we want to be between 7,100 and 7,600. Okay, and there's your picture. And my answer is 0.7705. 0.7705. So there's about a 77% chance that the sum of the 80 values is between 7,100 and 7,600. Questions? Again, it's almost what we did the last time we met with normal distribution, but you have to pay attention to whether you're using central limit theorem for the mean or central limit theorem for the sum. I did show you those differences, but I also have that on this last slide. Guys, I cannot caution you enough to pay attention and read carefully, because if you're asked to find the probability of an individual value, you don't use a central limit theorem at all. You just use the straight out normal distribution. If you're asked to find the probability of the sample mean, then we know we want to use the central limit theorem for the mean. And if you're being asked to find the probability of a sum or total, you want to use the central limit theorem for the sums. And again, I tried to kind of show that to you here in this comparison that we looked at earlier. But do you have questions? Okay, ladies, that kind of finishes that lesson. So the quiz for this particular topic is due by Sunday, I would think. I haven't looked.
I think it is Sunday.
I'm pretty sure it's Sunday.
I think it's Sunday as well.
I try to be consistent and keep it on Sunday. So we're in lesson 2, and it's a lesson on central limit theorem applications. So it will be quiz number 5, quiz 5, and I believe it is due on Sunday. It is. Yeah, it's due on Sunday.
Is it going to have any material for, should we wait to after Thursday, or
Nope.
should we go ahead and, okay.
You can go ahead and do it. We've covered all that material. On Thursday, I hope we will be talking about the next topic, which is confidence intervals and sample size estimation. Confidence intervals is a topic that we normally cover in Stat 1401. So hopefully that'll be a nice little review. But we don't usually talk about how to estimate the necessary sample size. And so that'll be kind of the new information for next class, but that's the plan.
And I think that's like what the next mini project is kind of.
I believe that's the next mini project. Yes, ma'am.
Okay, thank you.
You're very welcome. Other questions, ladies? All right, I will get the video processed and posted up, and I will I can send you guys the workspace too. I've got it saved. So y'all have a good afternoon.
Thank you, you too.
You're very welcome.